name is Georgia, and today I will be introducing you to a series of new spectacular species in organic chemistry called blatter radicals. There will be a succession of short videos going through what blatter radicals are, why they are special, how they are made, and where we can go from there. We're used to electrons existing in pairs, either within bonds or as lone pairs around atoms. When electrons are unpaired, the species are called free radicals. These are generally considered to be unstable and would react with water, air, and almost anything that happens to be in their path. This may be the case with some other free radicals, such as chloride radicals, which would lead to the depletion of the ozone layer, with a reaction kind of like this. Or other radicals in the body which can cause damage to cells, especially damage to DNA, which may play a role in the development of cancer or other serious health issues. However, blatter radicals are not like this. They do not deplete the ozone layer or cause cancer for all we know. Instead of blatter radicals being destructive, they have a myriad of potential applications across the scientific spectrum, from electronics and energy storage to biochemistry and single molecular devices. But why is this? What makes these species so stable and even desirable in future chemistry? In this series of videos, we will talk about stable organic radicals, diradicals, triradicals, about ferromagnetism and antiferromagnetism, about organic batteries, single molecular devices, and cancer, or rather, anti-cancer agents. But first, what are blatter radicals? These blatter radicals started off as part of the Chemical Research Division in New Jersey with a new stable free radical discovered by Herbert Blatter in 1968. This species had a structure similar to this. Blatter radicals are large aromatic compounds with one unpaired electron and lie within the scope of a large family of stable organic radicals. That's right, they are not the only ones. They're stable to the oxygen and the air we breathe, the moisture and heat. The three main ways to make the radicals more thermally or energetically stable are by, number one, increasing the delocalization of the unpaired electron over a large number of atoms. Number two, by having 3 electronegative nitrogen atoms in the trizine ring. And number three, through having electron withdrawing groups like the carbonyl group, nitro, or trichloromethyl. A planar system must be present in order to allow for delocalization of electrons. Therefore, it would make sense that, for example, by stopping the rotation along a bond like this somehow, there will be more delocalization and hence more thermally stable radicals. Another way of making the radicals less reactive is by physically stopping the reactant from reaching the unpaired electron, i.e. by steric hindrance. This decreases the rate of unwanted chemical reaction by having the steric bulk in the way of the reactive site. The strange thing about delocalization, however, is that it is not equally spread out throughout the molecule. From the structure of the molecule and the presence of 3 electronegative nitrogen atoms in the trizine ring, most of the electron density resides in that ring. We can think of the basic structure of the blatter radicals as having 3 functional aromatic sites around the trizine ring, site 1, 2, and 3. Aromatic site 1 is attached to nitrogen 1. Due to the steric effects of site 1 and the aryl ring, site 1 is tilted out of plane of the molecule, whereby the torsion angle varies due to the bulk of the rest of the molecule. This, in addition to the high electronegativity of nitrogen 1, results in little delocalization of the aromatic site 1. By contrast, since site 2 is in the same plane as the unpaired electron of the trizine ring, a large proportion of the unpaired electron can resonate here. In fact, owing to the high spin density, it is so reactive that if carbon-7 is not protected by any groups, it will oxidize to form the quinone structure. One way to prevent this is by adding an electron withdrawing group to carbon-7, like trichloromethyl, reducing spin density on carbon-7 and therefore reducing the reactivity even under really strong oxidative conditions, like permanganate. Finally, aromatic site 3 is attached to carbon-3. It is said to be spin isolated. This is because the unpaired electron cannot resonate to carbon-3, as can be seen by hand. Each of these aromatic sites provides different opportunities to alter the physical properties of the species. One simple example is that by increasing the delocalization of the unpaired electron over a larger number of atoms, pi conjugation increases. This results in a redshift in absorption to the near infrared region. Larger degree of delocalization leads to less energy needed for the promotion from the HOMO to the LUMO, and hence an increase in wavelength. Another such example is that of magnetic properties. Each electron in an atom has a magnetic moment that originates from the orbital motion around the nucleus and the spin of the electron. Depending on how the material responds to the magnetic flux, different magnetic properties can arise, where paramagnetic, ferromagnetic, and antiferromagnetic are the most common in radicals. Small structural changes, such as through the modification of substituents, can significantly affect the packing of the molecules, and in turn alter the magnetic properties of the radicals. And that is all for today's episode of the Blatter Radicals. If you were paying attention, you will now know more about Blatter radicals than most chemists in 1968, like what the general structures of the Blatter radicals are, their electron distribution, how increasing delocalization increases wavelength absorption, and how despite Blatter radicals having one unpaired electron, they do not destroy the ozone layer, or our DNA, for all we know. Until next time, with more Blatter radical chemistry.